Log on, tune in, find out. Another good idea from Cambridge.
From Sasha Vikhansky from Queen Mary, and I was going to read his title out, but on electrochemical system inversions. Off you go.
Okay. First of all, I want to thank the organizers for timing my talk at 9 o'clock after the dinner. So my talk is about identifiability. So basically what I'm going to talk about is much simpler than what most of people have presented so far. Let me start with an example. Say we have an electrode, a planar electrode, and there are two species, A and B, which can diffuse to the electrode and they react at the electrode. We have forward and backward reactions. Initially I assume that I have species A and species B are the product. And of course we have some other electrode somewhere at a remote distance, but it doesn't important for us. And the rate of the reaction between A and B is given by this expression. So we apply a voltage to the electrode, and then this rate of the reaction depends on the number of parameters, which the rate of the reaction is similar to the Arrhenius term, but instead of temperature we have voltage. So basically we have a pre-exponential factor. We have a sort of partition coefficient which is accounting for the asymmetry in forward and backward reaction. We have an equilibrium voltage, so if E is equal to E naught, then A concentration of A is equal to AB, and then there is resistance in the system which might slow down the reaction, and there is a capacitance in the system, right? And we apply, as I told, we apply the voltage and we measure a current at the electrode. The current consists of two parts: the Faraday current is due to the oxidation or reduction, and plus we have this current which is due to the capacitance and change of the voltage. So this system is quite typical for many experimental systems. So basically we have three types of the parameters. We have the parameters which we can control in the experiment. In this case, this is time series of the voltage which we apply. We have parameters which we can measure in the experiment. In this case, these are time series of current. And then we have parameters of the model which we want to estimate. So in principle, we can say that there is so-called output surface. So the measured parameters, they are function of the parameters of the model and the control parameters. And sometimes if I say that the design of experiment is fixed, I omit U, I just use this notation. Now, how we determine these parameters? The common wisdom says that, okay, if I have a model, I have experimental data, I minimize the difference, then the theta which minimizes the difference is the answer. And this is the illustration from some old book. This is voltammogram. So voltammogram is periodic, but for some reason they have only experimental data for half of the period, and you can see they fit it, and they say that the problem is solved. However, my experience is less, give me less optimism. These are results of my calculations. So you can see here, okay, this is the current as it measured, because we apply time-dependent voltage, so it has quite funny shape. And then I perform calculation with two sets of parameters. And please pay attention, the pre-exponential factor between these two cases varies by factor 3, about 300%. However, if you look on the difference between the signal in first experiment and the signal in the second experiment, which I denoted delta I, then you can see that this delta I is only maybe 10% out of the amplitude of the signal. It means that there is typical problem. We have very high variation in the parameters of the model and very low variation in the output. So practically it's very difficult to distinguish between this set of parameters and that set of the parameters. And why it happens. Let's come back to this idea of output surface, and let's consider the simplest case. We have only one theta, only one parameter we want to identify, and we measure two parameters, y1, y2. In this case, the output surface becomes just a curve in two-dimensional space, and theta is the parameterization of this curve. So when a system becomes unidentifiable, this is the first example, just intersection, so it means that there are two values of theta which gives the same output, right? Probably a more common case is this one. There is no intersection, and in principle, if we had infinitely precise measurements and correct model and infinitely accurate calculations, then we could identify everything. But in the reality, we always have an error. And say if you look on this part of this output surface or output curve, then you can see that, say in this case, you say, right, this point belongs to this part of the curve, so we can identify our parameter theta. But here, it's difficult to say whether it belongs to this part or that part, and the difference in theta is significant. And the last case, which is quite common, it's what happens if just there is low derivative or low eigenvalue of sensitivity matrix. Say a small variation of theta implies large variation of y. And so these are three examples. I think it's a complete list of all cases where a system is unidentifiable. At least I cannot offer any other scenario. And then it means basically that before we start any experiment, we have to answer this question, whether the system is identifiable. And yes or no is not a good answer. A better answer would be a quantitative answer, which says how much the uncertainty in the measurement affects the uncertainty in the identified parameters. Of course, if answer is yes, then we can do our experiments. However, with high probability, if we have more than two parameters, then the answer will be no. And in this case, we have two options. One, we can say, right, probably the system is over parameterized. So if we have too many parameters, it's quite common situation in biomedical applications. Then we have to restrict the number of parameters. So this is so-called problem of parameter selection. And the second option, we can say, no, every parameter is important. Then we have to add more experimental data, but then the question is what experiments we have to perform, because it might happen that we continue our experimentation, but new experiments don't produce any new information. So this is a so-called problem of experimental design. And it's what I am trying to present you today. So what's the basic idea? Let's introduce a characteristic for identifiability and say identifiability index, which is defined in this way. So theta 1 and theta 2 are two different sets of parameters. So this is the output under theta 1, this is the output under theta 2, and this function rho, in particular, you can consider it in this form, like just like distance between two sets of the parameters in the parametric space. So why I insist that this index gives us an indication about identifiability? Let's consider this case. Intersection means that this is non-zero, this is zero, so eta is infinity. The system is unidentifiable. In this case, what we have this difference is small, but this difference is not small. So eta is very high, right? System is maybe practically unidentifiable. Finally, if we are looking on local identifiability, we can expand in the Taylor series. It's quite simple. Everybody can do it. And the answer is that in this case, eta square is just equal to one of the smallest eigenvalue of the Fisher information matrix, which is a common measure for identifiability or unidentifiability. But the most important thing is that basically eta, if we write this expression in this way, basically eta gives us the upper bound for the error of identification of parameters. So if we say that this is our uncertainty in the measurements, then eta tells us how much this uncertainty is multiplied to be to affect the parameters we want to identify. So eta is just a factor which multiplies our error. And basically it means that as often happens in mathematics, I replaced one problem by other problem. Instead of solving a problem of identifiability, I have to find a maximum of a function, global maximum of a function. Basically this function is not convex, it might have multiply maxima, so it's not an easy problem. And I try to use a random search method, a special version of random search method, which is called SPSA, simultaneous perturbation stochastic approximation. This is a method which combines the ideas of gradient search and random search. So the idea is following: if I want to estimate a gradient of the function, I generate a vector with independent components delta I. I generate it only once, and then I calculate this finite difference. So I need to calculate only two. I have to calculate my function only twice. Doesn't matter what's the dimensionality of x, right? And then if I write this finite difference, the important thing is following: is that if I expand it into Taylor series, I have this component dh dxi, and then I have all other components like dh dxj delta j, and if I average this g, this gives me an estimate for the gradient. But if I look on this one, since these deltas are independent, if the distribution of deltas has finite negative moments, then on average this term is 0, so it means that this formula gives me an unbiased estimate for the gradient on one hand. On the other hand, due to the randomness, we have some hope that we might escape local extremums, and we can find global maxima. So then my algorithm is quite time consuming. So I solve partial differential equations for two sets of parameters. I evaluate my h, I generate this delta, I solve again the system of PDEs for two other sets of parameters, then I evaluate the gradient, and then I update my my parameters. So it means that in practice I have to solve my system of partial differential equations thousands and thousands of times, and although the system is quite simple, it's only one-dimensional PDE, although non-linear with stiff right-hand side. However, it's not a very difficult problem, but it takes about a couple of hours on desktop PC. And of course, since it's a random search, you have to repeat it many times to be sure that you indeed get the global maximum. And okay, this is illustration from the site of James Spall, the author of this method, how this method works. And this is an illustration. If you minimize a function, initially you have some oscillations, and then you oscillate around local optimum. And then let's come back to our electrochemical system. So usually in AC voltammetry, the signal, the voltage we apply to the electrode is following. We apply a triangular shape, and on the top of this triangle we add some high frequency signal, for example like this. Then the signal looks like this. And let's start with a particular case, called low resistance system. So as you probably remember, you have 6 parameters. 2 of them are resistance and capacitance. If resistance is low, then the capacitance doesn't play any role as well. So I have only 4 parameters. And then I try to estimate what's the identifiability of this system, what's the identifiability of these 6 parameters. And then this is the result of the calculation. So it appears that the error of the measurements is multiplied approximately by factor 9, which is tolerable because the precision of these measurements is quite high. And of course you can see what's the worst case, what's the 2 sets of the parameters which are more likely to be miscalculated in our situation. And of course they 2 correspond to high pre-exponential factor, because then it means that we have fast reaction. Fast reaction is difficult to identify. Now this is identifiability of the system. This factor says that okay, system is identifiable, but probably it can be made lower, and if we want to make it lower, then we have to come back to our problem, right? And then we have to remember that these y's are functions of theta, but they are also functions of the experimental design, which I denoted u, right? Then if I want to make this expression smaller, I basically have to solve a min-max problem, right? Again, global optimization, but now I'm looking for a saddle point. And if you say that the parameters of experimental design are amplitudes of these high frequency harmonics, then you can try to solve this problem by the same SPSA method, which is very well suitable for this type of problems. And these are results of my calculation. So what you can see here are classical waveforms which are used in voltammetry, because people have tried to find a good signal for a long time, and of course they have more experience in electrochemical systems than I have. And these are traditional waveforms, and this is my optimized waveform. So as all of these signals, it has a triangle shape plus a high frequency signal which has this shape. And indeed the identifiability parameter under this optimized signal is a little bit lower than in, if you remember, in the previous case, right? So on one hand, this signal is better than all classical signals. On the other hand, it's not a miracle that if people with experience try for a long time, they approach nearly optimum solutions. So the improvement is not very impressive because people have tried to do it for a long time. Now, every result I've shown so far, they are for low resistance system. Now, if the resistance is not small, so we have resistance and capacitance which play quite significant role, then whatever we have tried to do, we try to simulate multiply experiments where you have different scanning rates, so it's not just one experiment, by say 3 consecutive experiments with different scanning rate. All our attempts been unsuccessful, so the identifiability parameter is quite high, right? It means that AC voltammetry has a lot of problems with identification of all of these 6 parameters. As I told, one of the possibilities is to say that okay, system is over parameterized, we can at least restrict ourselves to a smaller set of parameters. And since we use a random search method, we of course have a lot of data, and then we can apply some statistical analysis to this data. In particular, you can use principal component analysis, so you can see the spread. This is a delta K. K is the pre-exponential factor. This is R. R is the resistance. The strong correlation between these two is quite obvious. If I have high pre-exponential factor, I have a faster reaction. However, high resistance means that reaction will slow down. So an increase in K can be compensated by a decrease in R. And well, the signs here are not important, because if I have the first set of parameters, second set of the parameters, if I change the order, then the sign will change. So what is important is the angle of inclination of this line, and not whether it increase or decrease. So by using principal component analysis, we can say, right, if we restrict ourselves on some sort of linear combination of R and K, we can identify at least these linear combinations. But it's only a partial solution. And what we have tried to do in last maybe half a year, we have tried to crack this nut. And the idea was following. So far, we have this system. We apply a voltage, we measure current. But we decide a priori what voltage we apply. Why don't we use this system? Why don't we use a feedback? In particular, why don't we use a feedback of this type with delay, right? Why we initially have chosen this feedback? Because the first idea was that the system becomes chaotic, right? And chaos is, of course, amplifies every initial error, right? But this initial idea wasn't very good, because yes, chaos amplifies every initial error, but it's very difficult to fit a chaotic trajectory. So we have tried to find some situation which is non-chaotic, but still what we call information rich. So these are results of example calculations. If I just perturb the system initially, and then I allow to the system to oscillate, then you can see that sooner or later it approaches a limit cycle. So this is I, this is E, but we have to remember that the dimensionality of the system is formally speaking, it's infinite. Anyway, the system lives in a fast space which has bigger dimension than 2. So what we see is just two-dimensional projections of these limit cycles. And then you can see that depending on the initial conditions, a system approaches, every time it approaches different limit cycle. In three-dimensional space, these limit cycles look like this. Probably it's difficult to distinguish between different limit cycles. However, the main idea is that we increase the dimensionality of the system. And then the experiment looks like this. We have this feedback control, and then we perturb our system by what's called a step voltammetry signal. So every time we increase voltage by one increment, see, and it's how this trajectory looks like. So this is because of these increments. And the trajectory is non-chaotic. How we know is simply vary the initial data and plot the variation in the initial data against the variation in the signal. You can see that it indicates that the system is not chaotic, because otherwise we had that this difference would be of the size of the attractor, right? So it's non-chaotic. However, it's what we call information rich. So this is the identifiability parameter, which is quite low, and this is identifiability parameter for the entire set of the parameters of the model. It means including the resistance and capacitance. Okay, these are my conclusions. I probably come back to this slide and discuss in a few words why we think that this approach with feedback control works. Because what this identifiability test basically means, we take two sets of parameters and then we say to our system, okay, cheat us. Find two sets of parameters which are more likely to be mistaken in the experiment, right? So basically, the computer code tries to fit two output signals, right, with two distant set of the parameters, right? Now, if this signal is in a low-dimensional space, then the computer code has enough controls to adjust these two signals, right? However, if the output signal is in a higher dimensional space, then we have the same number of control parameters, right? And it's much difficult to adjust these two signals. It's like, okay, if I drive a car, I have basically 2 degrees of freedom, right? But if I try to pilot an airplane, I need more degrees. I have more degrees of freedom, then I need more control parameters to pilot the airplane. And in this case, of course, the system doesn't have additional control parameters. It's why the identifiability is increasing so significantly. Yeah, that's it.
After that rather very interesting talk, any questions? There must be. That was so nice. So, I've got loads of questions because I was thinking about this. It's actually something that I've been working in a similar area. So, the first question, is identifiability, how is that related to well-posedness and ill-posedness?
Basically, yeah, you can call it this word. So if the system is identifiable, then it's well-posed. If it's unidentifiable, then it's ill-posed. Yes.
And then the other thing I was going to is a remark. I don't know. There's a very interesting literature in the engineering design literature on the global optimization of what they call expensive functions, where it might take many hours to do one function evaluation. And I don't know whether you know about this. It's they use response surfaces to fit the function. And then they work out they have a probabilistic model, and they work out which place is most likely to reduce the objective function.
Yeah, I know. I thought about different options to solve this global optimization problem. Why I stopped on SPSA? Because it's well, it's easy to implement. Well, you know, if you have a finite amount of resources, it's an argument. There is a theorem which says that this method converges if you run it for long enough time. Of course, if we want to make our algorithm more efficient, then it's better to combine this method with some local search method, which is non-random. It's one of the possibilities. The other possibility, which I am trying to push forward now, is to use some surrogate models.
Yeah, that's time for. Okay, well, let's thank Sasha once more.